Have you ever wondered how your computer can juggle like a million things at once and not even break a sweat? Well, the secret is one of the most important ideas in all of modern software, multithreading. And today, we're going to break it all down. I mean, just think about what's happening on your screen this very second. You might be watching a video, maybe an ad is loading on the side, and you're scrolling through the page, all of it happening at the same time, without a single hiccup. It seriously feels like magic. So how on earth does one single application do all of that at once? Well, that magic has a name, multithreading. It's the engine that makes modern software feel so incredibly fast and responsive. It's the reason our apps can handle so many different jobs at the same time, giving us that seamless experience we all just expect now. Okay, so let's get right to it. What exactly is a thread? To really get multithreading, we've got to start with the most basic building block, the absolute smallest unit of work a computer can handle. A thread is basically the smallest possible sequence of instructions that your operating system can manage on its own. So think of it this way. If your entire web browser is one big process, then inside that process, you've got lots of little threads running around. One thread might be playing the video, another is busy loading images, and a third is just waiting for you to click your mouse. But here's the crucial part. They all share the same memory. And that is the secret to their power. This table really lays it all out, doesn't it? Just look at the rows for memory and communication. A process has its own separate private memory space. That makes it really isolated and safe, but it also makes it super expensive to create and really slow to communicate with. Threads, on the other hand, share their memory. They give up a little bit of that safety for just incredible speed and efficiency. That one difference is pretty much the whole reason multithreading is so powerful. So that comparison leads us right to a term you'll hear thrown around all the time. People always call threads lightweight processes. But what does that actually mean in practice? You guessed it, it all comes back to that shared memory. See, creating a brand new process means the operating system has to go find and set up a whole new isolated chunk of memory. That's a really slow and expensive operation. Threads, they just skip all that. They reuse the memory that the process already has, which makes creating them, switching between them, and getting rid of them insanely fast. That's the lightweight advantage. And get this, here's a fact that might actually surprise you. Multithreading isn't some fancy advanced feature you have to turn on. In a lot of modern environments, like Java for example, it's just the default. Even the simplest Hello World program actually has multiple threads running in the background, doing things like cleaning up memory. It's happening all the time, whether we realize it or not. Okay, so we know what threads are. Now for the fun part. What do they actually do for us? Why is this whole idea of concurrency so important for the software we use every single day? Oh, the benefits are just huge. For you, the user, it means the app is responsive. Any long-running task, like downloading a big file, gets pushed to a background thread, so your user interface never freezes up. For the computer itself, it means we're actually using our powerful multi-core CPUs to their full potential, instead of just letting them sit around doing nothing. And for developers, it means we can build massive systems, like web servers, that can handle thousands of users all at the same time. But here's the thing, you can't just sprinkle threads on every problem and hope for the best. You really have to understand the kind of work you're doing. A CPU-bound task, something like heavy-duty image processing, is all about raw processor speed. But an I/O-bound task, like downloading a file from the internet, spends most of its time just waiting. And this is where the strategy matters so much. For those waiting tasks, having more threads is fantastic, because while one is just sitting there waiting, another one can jump in and use the CPU. And once you know what to look for, you start seeing this pattern absolutely everywhere. Your browser uses threads to keep the user interface separate from all the network requests. The web server that browser's talking to, it's probably spinning up a new thread for every single user request. Even the code editor that a developer uses depends on background threads for stuff like spell checking, just so that the typing experience stays perfectly smooth. So multithreading sounds like a silver bullet, right? It seems perfect. But with any really powerful tool, there's always a catch. And the very thing that makes threads so efficient, that shared memory, is also the source of their biggest dangers. So yeah, while threads are lightweight, they're not exactly free. Switching between them still costs a little bit of time, and each one needs its own little piece of memory for its own stuff. But the real problem, the thing that gives developers headaches, is the complexity. Bugs in multi-threaded code are a total nightmare to find because they're random. They might only pop up when the threads execute in one very specific, very unlucky order. And this leads us to a really crucial point that seems completely backward at first.
adding more threads doesn't always make your app faster. If you go too far, the CPU starts spending more time just managing and switching between all the threads than it does doing any actual work. And that overhead can grind your whole system to a halt, making your app even slower than if you had just used one thread. So the biggest dangers all come from that shared memory. When you have multiple threads all trying to read and write to the same piece of data at the same time without any kind of coordination, you can run into two classic nightmare bugs.
First up is the infamous race condition. This happens when your final result depends entirely on which thread wins the race to get to the data first. Imagine two threads are both trying to increase a counter, let's say, count plus plus, at the exact same time. You'd expect the number to go up by 2, right? Well, not so fast. See, that simple little count plus plus operation isn't just one single action to the computer. It's actually 3 separate steps. Read the value, add 1 to it, and then write the new value back. So picture this. Thread A reads the value, which is 5. But before it can write 6 back, the system switches over to thread B, which also reads 5. Now eventually, both threads will write 6 back to memory. The counter only went up by 1 instead of 2. You've literally lost an update, and now your data is wrong. The second monster you have to watch out for is a deadlock. This is like a digital traffic jam where nobody moves. Imagine thread A has locked a file that thread B needs to use. At the same time, thread B has locked a database record that thread A needs. Neither one is going to give up what it has, so they both just wait forever, and your application just freezes solid. So, with all this incredible power and all this incredible danger, what's the big takeaway here? How are you supposed to use this tool without, getting burned? Well, it all comes down to one golden rule. And the golden rule is this: do not add multi-threading unless you actually need concurrency. It's that simple. If your task can be done in a simple, straight line, just keep it that way. You only bring in all the power and all the problems of multi-threading when you absolutely have to do multiple things at once, like keeping your app responsive while a big download happens in the background. At the end of the day, multi-threading is really a double-edged sword. It's the tool we have to use to boost performance and make our software feel modern and fast. But the very source of its power, that shared memory, is also its greatest risk, opening the door to a whole category of really tricky, unpredictable bugs. The real skill isn't just knowing how to use multithreading, but knowing when to use it. And with that in mind, what's something you do every day that you now realize is totally
All right, let's talk about something that comes up in pretty much every single Java interview: creating threads. Now, it sounds basic, right? But trust me, how you answer this one question can make or break your chances. It's a huge tell. So let's get right into it.
So, picture this. You're sitting in that interview chair, and the interviewer leans in and asks, "How do you create a thread in Java?" Seems easy enough, doesn't it? But oh man, the way you answer this tells them so much about how deep your Java knowledge really goes.
Yeah, because it's not really about just spitting out some code. Your answer is like a time machine. It shows the interviewer whether you're stuck back in the early days of Java or if you're up to date with the modern, super efficient ways of doing things. It's a test of your understanding of Java's evolution.
So let's start at the very beginning, with the 2 original methods for creating threads. You can think of these as the absolute building blocks that every Java developer learns first.
The first, and the most direct way, is to just make a class that extends Java's built-in thread class. This is probably the very first thing you ever saw in a textbook about threads.
And it looks super simple, right? You just make a class, say myThread, and have it extend the thread class. You dump all your logic inside the run method, then you just create a new myThread object and call .start. Boom, new thread, easy peasy.
But, and this is a huge but, simple isn't always good. Here's the killer problem. Java only has single inheritance. So the second your class extends thread, that's it. It can't extend anything else, ever. You've completely locked it down. Plus, your task, the actual work you want to do, is now permanently stuck to the thread itself. It's what we call tight coupling, and in software design, that's a big no-no.
So the verdict here is pretty clear. While you absolutely have to know this method exists, you would never, ever use it for real production-level code. It's purely a legacy approach. To fix all those problems, Java gave us a much, much better way, implementing the Runnable interface. And honestly, this was a huge leap forward for good software design. Now look at this, it's a game changer. Our class, myTask, isn't a thread anymore. It's just a task, a piece of work. It implements the Runnable interface. Then we take that task and hand it over to a real thread object. You see what we did there? We separated the work from the worker.
And that separation is what makes it so powerful. Your task class is now totally free to extend some other class if you need it to. This is just fundamental object-oriented design, and it's why all the modern frameworks like Spring, for example, pretty much demand this approach. And here's the money line for your interview. You say this, and they'll know you get it. Runnable decouples what to do from how to execute it. I mean, just look at them side by side. It's not even a contest. When it comes to good design, inheritance, flexibility, Runnable wins every single time. It's just a way more professional and flexible approach. And if you want to sound extra smart, this is the core principle at play. It's composition over inheritance. We're composing a thread with a runnable task instead of locking ourselves into that rigid inheritance chain. It's just better software engineering. Okay, let's fast forward a bit. In Java 5, everything changed. I mean, it was a total revolution for concurrent programming with a whole new toolkit of high-level utilities. The first of these awesome new tools is the Callable interface. Think of it like Runnable's bigger, stronger sibling. It was designed to solve two major headaches that Runnable had. So what are those two headaches? Well, first, Runnable's run method returns void. It can't give you a result back. Callable's call method can. And second, run can't throw checked exceptions, which is a real pain for error handling. Callable, on the other hand, totally can, which makes your code so much cleaner. So you might be asking, if a callable can return a result, how do I get it? The answer is an object called a future. When you go to run your callable, you don't wait for it. You immediately get back a future. It's like a receipt or a promise that the result is coming later. You can use that future to check if the job is done, or to just sit and wait for the final result to pop out. And all of this leads us to the fourth, the final, and let's be clear, the absolute best practice in modern Java today, the executor service. Okay, so this is where the entire mindset shifts. We stop thinking about creating one thread at a time. Instead, we think about managing a pool of worker threads. And that's exactly what an executor service does. It's like a manager that handles all the grunt work for you, creating threads, managing them, and this is the most important part, reusing them. Why is that a big deal? Because creating a new thread from scratch is actually a really expensive operation. Reusing existing ones is way, way faster. It's a massive performance boost, and it stops your application from just spinning up thousands of threads and crashing the whole system. And that brings us to the modern rule of thumb. For any serious real-world application, you just don't create threads by hand anymore. You always use the ExecutorService framework, period. Okay, so we've got the 4 methods down, but a good interviewer is going to hit you with a follow-up. They love this one because it shows if you actually understand what's happening under the hood. The question is, what really happens when you call the start method? Let's break it down. When you call start, you are not calling your run method. What you're really doing is telling the Java virtual machine, hey, I need a new thread. The JVM then talks to the operating system, gets a brand new native thread, sets up a fresh call stack just for it, and then marks it as ready to go. Only then does the JVM call your run method for you, but it makes sure it executes on that new, separate thread. And this right here, this is the classic interview gotcha question, the one they use to trip people up. If you call t.start, you're kicking off real, actual multithreading. But if you call t.run directly, no new thread, not at all. You're just calling a method. It runs right then and there on the current thread, just like any other method call. It's not multithreading. It's just a plain old function call. All right, here's another quick one they might throw at you. What happens if you try to call start on the same thread object a second time? The answer is a hard no. A thread can only be born once. Once it's started and finishes its job, it's done for good. You can't restart it. If you try, Java will immediately throw an illegal thread state exception right in your face. Okay, let's put a bow on all of this. We've gone from the old school ways to the modern best practices. So how do you wrap all this knowledge into the perfect, job-winning interview answer? Your definitive answer is always to use the executor service. You explain that you define your tasks as either runnable or callable objects, and then you'd submit them to the service. Why? Because it gives you the absolute best performance, fantastic resource control, it scales beautifully, and it's just the safe, professional way to build a real application.
So at the end of the day, this whole thing tells a story, doesn't it? The story of how Java grew up. It went from this very manual, low-level way of doing things to this super smart, high-level executor framework. And the whole reason for that journey? To give us better performance, way better scalability, and a much safer way to write concurrent code. So when you're in that interview, it's not just about listing the 4 ways. It's about showing you understand why this evolution happened.
All right, if you've ever prepped for a Java interview, you know that sinking feeling when multi-threading comes up. Those questions can be brutal. Well, today, we're going to tackle that head-on. We are going to master the Java thread lifecycle so you can walk into that interview and absolutely nail those questions with confidence.
And it almost always comes down to this question right here. Seriously, this is the one. Interviewers love this question because it's the perfect filter. It instantly separates the people who just memorize some flashcards from the ones who actually get concurrency. It looks simple on the surface, but trust me, the why behind it, that's where everything is revealed.
So that's our mission today. We're going to break it all down. We're not just going to give you the answer, we're going to build it from the ground up, starting with a thread's entire life story. Because once you see that full journey, the whole wait versus sleep thing, it's going to click. It'll be totally clear.
Okay, so the best way to think about a thread's lifecycle is like it's a map. You've got this main highway, the simple path, and then you've got these tricky little detours and side roads. We're going to start with the main highway. Let's get that down first. The simplest, most direct route a thread can take from the moment it's created to the moment it's gone.
And that main path is just 3 steps. Super straightforward. A thread is born, that's new. It gets ready to do some work, that's runnable. And then its job is done, it's terminated. New, runnable, terminated. Let's zoom in on each one. So, when a thread is in the new state, think of it as just, well, an idea. It's nothing more than a plain old Java object. Yeah, the JVM has set aside some memory for it, but the actual operating system? It has no clue this thread even exists yet. It's like a blueprint for a house that hasn't been built.
And here's what that looks like in your code. Just this one line. The moment you write new thread, you've done it. That thread object, T, is created. And right there, at that exact instant, before you even think about calling start, that thread is just sitting there, chilling in the new state.
Okay, now things get interesting. When you call start, the thread moves into the runnable state. But hold on, because here's a classic interview trap. You might think runnable means it's running, right? Nope. The JVM actually lumps 2 things together here, a thread that's ready to run and a thread that's currently running.
That's right. It's a super common misconception. People assume there's a separate running state, but if you look at Java's actual thread.state enum, it's not there. So a runnable thread could be one of 2 things. It could be firing on all cylinders, executing code on a CPU core right now, or it could just be hanging out in a line, waiting for the operating system scheduler to give it a turn. As far as the JVM is concerned, both of those situations are just runnable.
And that brings us to the end of the road, the terminated state. Once that run method finishes its job, whether it completes successfully or crashes with an exception, the thread is done. It enters terminated. And that's it. It's permanent. You can't bring it back to life. You can't restart it. Game over. Its story has been told.
All right, so we've navigated the main highway. Easy enough. But now it's time for those tricky detours I mentioned, the waiting states. And let me tell you, this is where interviewers really try to trip you up.
There are 3 of them, and they cause so much confusion. Blocked, waiting, and timed_waiting. On the surface, they all sound similar, right? The thread is paused. But the reason it's paused and what it's waiting on, that's totally different for each one. So let's untangle this mess one state at a time. First up, blocked. This one is super specific. A thread enters the blocked state for one reason and one reason only. It wants to get into a synchronized block or method, but some other thread is already in there, holding the lock. That's it. It's not waiting for a signal, it's not taking a nap, it's actively trying to barge through a locked door.
Next, we have the waiting state. Now, this is all about teamwork and coordination. A thread goes into this state on purpose by calling something like object.wait or thread.join. It's basically saying, hey, I'm going to sit here and wait indefinitely until another thread gives me a specific signal, usually with a notify or notifyAll call.
And finally, there's timed waiting. This is pretty much exactly like the waiting state, but with an escape hatch, a timeout. This happens when you call methods that have a time limit, like thread.sleep1000 or object.wait500. The thread is waiting, but it's not going to wait forever. It'll wake up if it gets that notification or if the clock runs out, whichever happens first. Okay, let's put blocked and waiting side by side, because this distinction is absolutely critical for your interview. Remember, blocked is about fighting for a lock that someone else has. Waiting is about politely waiting for a signal. But here is the single most important difference. A blocked thread holds on to any locks it already has. It's greedy. A thread that calls wait, on the other hand, releases the lock on the object it was waiting on. It plays nice.
And if you want a killer soundbite for your interview, this is it. Write this down. Blocked is about lock acquisition. Waiting is about coordination. One is a fight for a resource, the other is a cooperative handover. It's simple, it's powerful, and it shows you get it.
So, with all that background, with our map of the thread lifecycle complete, we're finally ready. It's time for the main event. We're going to tackle that big question, the one we started with. Let's do the showdown, sleep versus wait.
Okay, your high-level elevator pitch answer is this. Sleep is just a pause button. It's simple. It just tells the thread, hey, take a break for a bit. But wait is way more sophisticated. It's a tool for communication, for getting threads to work together.
But let's go deeper. First off, where do they live? Sleep is a static method on the thread class itself. Wait, weirdly, is a method on the base object class. We'll get to why in a sec. Also, you can call sleep anywhere, but wait, you have to call it from inside a synchronized block. But again, the absolute #1 game-changing difference comes down to the lock.
And this right here is the golden nugget, the key takeaway. Sleep holds the lock, wait hands it over. Say that again. Sleep holds the lock, wait hands it over. If a thread is in a synchronized block and calls sleeping, it falls asleep, but it keeps a death grip on that lock. No one else can get in. But if it calls wait, it releases the lock on its way into the waiting room, letting another thread come in and take its turn. It's a fundamental difference in behavior.
This naturally leads to the next level senior dev question. Okay, so why is wait on the object class and not the thread class? And the answer is, well, it's just beautiful, elegant design. See, in Java, any object can be a lock. The whole point of wait is to release the lock on a specific object you're waiting on. So the method has to be on the object that has the lock. If wait was a method on the thread class, and that thread held, say, 5 different locks, how would the method know which one to release? It couldn't. Putting it on object makes it unambiguous. You're always releasing the lock of the object you called wait on. It's clean, it's safe.
Okay, so we've done it. We've mapped out the entire life cycle, we've broken down the toughest interview question, but so what? Why does any of this matter once you've got the job? What's the actual real-world payoff here? Here's why. Every single time you're trying to figure out why an application is slow, or why a service is totally frozen, or why you have a deadlock, you are debugging the thread lifecycle. That performance problem, it's probably a bunch of threads stuck in the blocked state, fighting for a lock. That deadlock, that's just 2 threads, each blocked, waiting for a lock the other one holds. That weird memory leak, it could be a thread that went into the waiting state and never got the signal to wake up. This stuff isn't just theory. It's your fundamental toolkit for diagnosing the gnarliest production issues.
And that's where I want to leave you. Knowing the states is the first step. Applying that knowledge is the real challenge. Now that you understand these states, blocked, waiting, runnable, you have the building blocks to solve some really hard problems. So think about this. How could you use what you now know to design a system that could detect a deadlock in real time? How could you build a tool to find these problems before they crash your entire application? That's where this knowledge really becomes powerful.
Let's talk about one of the most misunderstood parts of Java, thread scheduling. We're going to bust some myths today, some really common and honestly kind of dangerous assumptions that can lead to some seriously buggy and unpredictable code.
Okay, so let's just jump right in with a question. You've got a super important task. You spin up a thread for it, and you crank its priority all the way up to the max. That means it's guaranteed to run first, right? Well, if you're nodding along, you're going to want to stick around because the real answer might just surprise you. All right, first things first, let's get on the same page. What even is thread scheduling? Well, you can think of it as the traffic cop for your CPU. It's the system that looks at all the threads that are ready to go and decides, okay, you get to run now, and you get to run for this long. But that brings up the million-dollar question. Who is this traffic cop? Is it the Java virtual machine, or is it something else entirely? The best way to think about it is this. The JVM proposes, but the operating system disposes. And this slide really breaks it down. See, the JVM is in charge of its own little world. It manages all the threads and decides which ones are in the runnable state. Basically, which ones are ready and waiting in line. But the final call, The actual decision to put a thread on a CPU core and let it run, that power belongs completely to the operating system.
So, knowing that the OS has the last word, it leads to our first big myth. As a Java developer, can you just reach in and force the scheduler to run your threads in the exact order you want?
And the answer to that is a big, fat, unambiguous no. You have zero direct control. In fact, the Java specification was written specifically to not make any promises about execution order. Now, what we can do is try to influence it. We can give it hints. We've got methods like set priority, yielding, or sleeping that basically let us say, hey, scheduler, it would be really great if you did this. But, and this is the most important part, the JVM and the OS are totally free to look at our hint and just ignore it. So let's zoom in on the most popular and definitely most misused of these hints, thread priority. The absolute key here is to get it out of your head that this is a command. It's not. It's just a suggestion. I mean, look at the official definition. It says it all right there. It's a hint about the relative importance of a thread. It's all about trying to nudge the scheduler to say, hey, this one is kind of more important than that one, not to order it around.
And in Java, we give this hint with a simple number from 1 to 10. By default, every new thread you create starts out right in the middle at 5, which is norm priority. Fun fact, a new thread just inherits whatever priority its parent thread had, unless you go in and change it yourself.
Okay, so this brings us back to that very first question, the big one. If I make one thread a priority 10 and another one a priority 1, is it an absolute guarantee that my priority 10 thread will run to completion before the priority 1 thread even gets a chance? Absolutely not. And I can't stress this enough. This is probably the single most dangerous assumption you can make when writing concurrent code in Java. There are zero guarantees. A higher priority thread might not run first. A lower priority thread might get CPU time before a higher priority one. It's a total toss-up.
So here it is, the one-liner I want you to tattoo on your brain. If you forget everything else from this explainer, remember this. Priority is a suggestion, not a command. Nailing this concept is the key to writing concurrent code that doesn't fall apart.
Okay, so why? Why is it just a suggestion? Why is it so darn unreliable when you get down to it? Well, it turns out there are some pretty powerful forces at play that can completely override whatever hints we try to give. It really comes down to 3 main things. First, the OS scheduler can just decide to do its own thing. Second, things are wildly different depending on what system you're on. For instance, Windows actually pays pretty close attention to thread priorities. But Linux, it might take all 10 of those Java priority levels and just squash them down into a couple of its own. And finally, the JVM itself is always running its own crazy smart optimizations that can totally change the game. So, if we can't depend on priority or yield or sleep to make sure our code actually works correctly, what are we supposed to do? Let's open up the professional's playbook and see how you write concurrent code that is solid and predictable.
The right way, the only way, is to never, ever, ever build your program's correctness on these scheduling hints. Instead, you have to use the real tools of concurrency. We're talking synchronization blocks, the super robust executor framework, or things like fair locks if you really do need a first in, first out kind of ordering. These tools give you guarantees. Priority just gives you hope. So let's wrap all this up by asking one last really important question. Why is Java even built like this? Why all the uncertainty? It might feel like a mistake or a flaw, but it's actually a super critical feature. You see, this non-determinism, this lack of guarantees, it's 100% on purpose. By not forcing the JVM and the OS into a rigid, predictable scheduling model, Java gives them the freedom to make amazing optimizations under the hood. This very flexibility is a huge part of what makes modern systems so fast and efficient. And that brings us to the golden rule, the ultimate takeaway for Java concurrency. A correct, multi-threaded program is one that works no matter what the scheduler decides to do. It must never, under any circumstances, rely on a specific execution order or a thread's priority to function correctly. So, I'll just leave you with this final thought. Now that you know thread scheduling is really a world of suggestions and not commands, how is that going to change how you write and, more importantly, how you debug your next multi-threaded application? It's definitely something to think about. Thanks for watching. All right, let's talk about one of the most critical topics in Java, synchronization. Seriously, if you're building any kind of multi-threaded app or you're gearing up for a technical interview, you have to get this right. It's all about making your code work correctly when multiple things are happening at once. So let's just dive right in. So I want to start with a question that seems almost too simple. You look at count++. It's one line. It's basic. What could possibly go wrong with that? Well, it turns out that in a multi-threaded world, that one innocent-looking line is a ticking time bomb. But why? Okay, so before we can talk about the solution, we have to get a really clear picture of the problem. We're going to look at something called a race condition, and we'll see how a super simple counter can just completely fall apart. Check out this counter class. It couldn't be simpler, right? Now imagine two threads. Let's call them thread A and thread B, both trying to call increment at pretty much the same time. Let's say the count is at 5. Thread A reads the value 5. But hold on. Before it can add 1 and save it, the CPU scheduler pauses it and switches over to thread B. Now thread B comes in, and what value does it read? It also reads 5. So thread B adds 1, writes 6 back. Then thread A wakes up, remembers it had a 5, adds 1, and it also writes 6. We called increment twice, but our count only went up by 1. Poof! An entire operation just vanished into thin air. That, right there, is a race condition. So that's the chaos. How do we fix it? How do we stop our threads from stepping all over each other and corrupting our data? Well, the answer in Java is synchronization. This is the tool we're given to bring order back from the chaos and make our code what we call thread safe. All right, if you're in an interview, this is the definition you want to have in your back pocket. Think of synchronization as a traffic cop for your code. It stands in front of a shared resource, like our account variable, and only lets one thread in at a time. The whole point? To make sure our data stays consistent and predictable. But why do we even need a traffic cop? Well, it's because all of our threads are basically playing in the same sandbox, the heap memory. And that little count++ operation, it's not one single action. The CPU sees it as 3 steps. First, read the current value. Second, add 1 to it. And third, write the new value back. The CPU can hit pause between any of those steps, letting another thread jump in and cause mayhem. And the result is always the same: messed up data and a program in a corrupted state. Now here's a killer line for an interview. Synchronization gives you 2 big promises. The first is mutual exclusion. That's our traffic cop, right? Only one thread gets access at a time, mutually exclusive. But the second one, visibility, is just as important. It guarantees that when one thread makes a change inside a synchronized block, other threads will actually see that change right away. No stale data. So this brings us to a key concept, the critical section. This is the specific chunk of your code that's actually touching the shared data. Your job as a developer isn't just to slap synchronized on everything. It's to be a surgeon. You need to identify the absolute smallest, most precise block of code that needs protection. That's how you keep things safe without killing your performance. Okay, so we get the what and the why. Now let's get into the how. Java doesn't just give us one tool. It gives us a few different ways to implement synchronization. And, choosing the right one is absolutely essential for getting that balance between safety and speed. You've basically got 3 main options in your toolkit. You can synchronize an entire method. You can just synchronize a specific block of code inside a method, which, spoiler alert, is usually the better choice. Or you can use something called static synchronization for static data. Let's see how they compare. This table kind of says it all, doesn't it? Synchronizing a whole method is easy, sure, but it's like using a sledgehammer to hang a picture frame. You lock the entire method from start to finish, even the parts that don't need locking. A synchronized block, on the other hand, gives you that surgical precision. You wrap only the critical lines of code, which leaves the rest of the method free for other threads, and that means way better performance and a lot more flexibility. So this is the golden rule. Seriously, burn this into your brain. The mark of a great concurrent programmer is making your critical sections as small and as fast as humanly possible. This is exactly why synchronized blocks are almost always the way to go. It shows you understand that trade-off between keeping things safe and keeping things fast. Okay, but when we say we lock something, what are we actually locking? Well, there are 2 fundamental types of locks. There's an object lock, which is tied to a specific instance of an object. Think this. You use that to protect instance variables. But what if your data is static, meaning it's shared across all instances of a class? For that, you need a class-level lock. If you use the wrong one, guess what? You've got 0 protection. So we've been throwing this word lock around a lot. But what is it really? Let's pull back the curtain for a second and look at the magic that makes this all possible. It's called the intrinsic lock. This is honestly such a cool concept. Every single object you create in Java comes with its own secret built-in lock. It's sometimes called a monitor lock. It's just there, waiting. And the synchronized keyword is basically the magic command that tells a thread, hey, go grab that object's built-in lock before you proceed. And when the thread leaves the synchronized section, it automatically releases the lock for the next thread in line.
Okay, quick pap quiz to see if you're following. Let's say thread A gets a lock on counter object 1, and thread B gets a lock on a totally separate counter object 2. What happens then? Do they block each other?
The answer is a big no. And this is so important to understand. They don't block each other at all. Think about it. They're like two people with two different keys trying to get into two different houses. There's no conflict. Each thread has the lock for its own specific object instance. This just proves that the lock is tied to the object, not the class as a whole.
Okay, you've got the fundamentals down solid. Now let's talk about where people tend to get tripped up. These are the tricky questions and common mistakes that you're almost guaranteed to see in a technical interview about concurrency.
And here it is, the absolute classic Java interview question. You're sitting across from the hiring manager, they lean forward, and they ask you, can you put the synchronized keyword on a constructor? What do you say? The answer is a simple, confident, and emphatic no. And here's the simple reason why. Synchronization needs a lock, right? And a lock belongs to an object. But what's the whole point of a constructor? Its job is to create the object in the first place. The object literally doesn't exist yet when the constructor is running, so there is nothing to lock. It's a logical impossibility. If you need to control the creation of objects safely, you use other patterns, like a synchronized static factory method.
And beyond the constructor trap, there are a few others to watch out for. The biggest one is just being lazy and synchronizing huge chunks of code, which just kills your performance. Other classic mistakes include grabbing the wrong lock, like using an instance lock for static data, or just blindly using synchronized this everywhere without actually thinking if this is the correct object to be locking on. And that really brings us to the core idea, the big takeaway from all of this. Synchronization is a trade-off, plain and simple. You are trading some of your application's concurrency, its ability to do things in parallel, in exchange for a guarantee of correctness. A good engineer knows how to use synchronized. A great engineer knows how to design their code to need as little of it as possible by keeping those critical sections tiny. So we'll end on this thought. You now have the tools, and you understand the principles behind writing correct, thread-safe Java code. But the real art, the real challenge, is in the application. So the question I'll leave you with is this. In your next project, how are you going to strike that perfect balance between safety? All right, let's dive right in. Today, we are tackling one of the trickiest, but also one of the most critical topics for any Java developer, inter-thread communication. Honestly, if you can nail this, you are going to stand out in any technical interview. So just imagine for a second, you're in that high-stakes technical interview, the final round. The pressure is on, but you've been crushing every question they've thrown at you. And then, this is the question that lands on your desk. This is that moment, you know? It's what separates a pretty good candidate from a great one. But don't you worry, we are going to build the perfect answer together, step by step. Okay, so first things first, you need a really strong foundational answer. This is how you're going to open with total confidence and clarity. You want to start with a definition that's just clean. Something precisely like this. It's accurate, it's to the point, and it shows the interviewer right away that you get the main idea. It's all about coordination. The next question in your head should be, okay, but why do we even need this? And the answer, really, is to prevent absolute chaos. Without this coordination, you get threads that either spin around uselessly, wasting CPU cycles, that's called busy waiting, or even worse, they process data in the wrong order, which leads to some seriously wrong results. And hey, if you really want to impress them, this is the line to use. It just reframes the whole concept in such a smart way. It's not about threads fighting over resources. It's about them working together as a team. So how does this cooperation actually happen? Well, it all comes down to these three core methods, which, interestingly enough, live in Java's object class. You've got wait, which tells a thread, hey, take a break and let go of the lock. Then there's notify, which wakes up just one single random thread. And finally, notifyAll, which, you guessed it, wakes up every single thread that's waiting. Okay, so that's your rock-solid opening. But a truly great candidate, they don't stop there. The tough follow-up questions, that's where you really get to show that you have a deep, practical understanding of how this all works.
And here it is, the classic follow-up. This one is designed to test if you really understand the relationship between threads, the objects they work on, and the locks that protect them. And bam, here's your perfect pungy answer. See, these methods, they operate on an object's monitor lock. And since basically any Java object can be used as a lock, these methods have to be in the object class so they're available everywhere. A thread doesn't own a lock, it acquires a lock on an object. It's a subtle but crucial distinction.
Okay, next up, they're probably going to ask about the difference between waking up one thread versus waking up all of them. The choice you make here can have some major consequences for how your application behaves. Now, this table is super helpful because it really breaks down the trade-offs. With Notify, you're kind of rolling the dice, right? You have no idea which thread is going to wake up. If the wrong one gets the signal, you could have a big problem, like a system stall. NotifyAll, on the other hand, is just safer. It makes sure that the right thread will eventually get a chance to run. Yeah, it might create a little more competition for the lock right after, but safety usually wins. The general rule is, when in doubt, just use NotifyAll.
Okay, this next idea is a little weird, but it's absolutely critical. Get this. A thread can just wake up from a wait call for no apparent reason. It's not a bug, it's a feature. It's rare, but the JVM is allowed to do it for performance reasons. And that weird possibility that a thread can just wake up for no reason leads directly to probably the most important follow-up question you'll get. Seriously, this is one of the biggest interview traps on this topic.
And this slide just lays it out perfectly. You never, ever, ever call wait inside a simple if statement. It has to be inside a while loop that's checking the condition you care about every single time. Non-negotiable.
So why is that so important? Well, think about it. If that thread wakes up spuriously for no reason, the while loop forces it to go back and check the condition again. If the condition still isn't true, it just says, nope, back to sleep, and calls wait again. This simple little loop is your shield against spurious wakeups and all sorts of other nasty race conditions.
All right, so we've got the theory down. Now let's make this real. Let's apply all this stuff to one of the most famous problems in all of concurrency. I'm talking, of course, about the producer-consumer problem. This is like the textbook case for inter-thread communication. You've got some threads making stuff, you've got other threads using that stuff, and they're communicating through some kind of shared space, like a buffer. The whole puzzle here is about coordination, right? How do you get the producer to just pause when the buffer's full? And on the flip side, how do you get the consumer to wait patiently when the buffer's empty? The answer, as you now know, involves wait and notify all.
Okay, here's a really crucial point. Knowing all this wait and notify stuff is vital for passing an interview. But in the real world, on a real project, there's a much, much better way to solve this exact problem.
And that better, smarter way is to use something from Java's own concurrency library called a BlockingQueue. This is a higher-level tool that does all the hard work for you. So why is it so much better? Simple. It handles all that messy, error-prone coordination for you. All those synchronized blocks, those while loops with wait calls, the notify all calls, it's all baked right into the BlockingQueue itself. It was written by concurrency experts, it's been tested to death, and it's way less likely to have those subtle bugs that are so hard to find. The easiest way to think about this is with a conveyor belt analogy. Imagine your app as a factory. You have a producer worker putting items onto the belt and a consumer worker taking them off the other end. The conveyor belt itself is the BlockingQueue. Now, if the belt gets full, the producer worker just automatically waits. And if the belt becomes empty, the consumer worker waits. The belt handles all that logic for them. It's that simple. Okay, before we finish up, let's quickly go over the big mistakes, the common traps you want to avoid at all costs. Knowing these will help make sure you don't stumble at the finish line. Trap number 1, and this is a big one, you have to, absolutely have to, own the lock on an object before you call wait or notify on it. If you forget to wrap your call in a synchronized block, your app will just crash with an illegal monitor state exception. And trap number 2 is just being careless and using notify when you shouldn't. Like we talked about, if you have a bunch of threads waiting for different conditions and the wrong one gets woken up, your whole system can just grind to a halt. Notify all is almost always your safer bet. And finally, this is how you stick the landing. You wrap it all up with a strong, confident, and pragmatic closing statement. A summary like this shows you don't just understand the low-level theory, you also know how to apply it wisely in a modern professional setting. You've just proven you're not just a coder, you're a thoughtful engineer.
Welcome to The Explainer. Today, we are going to tackle one of those classic computer science problems. You know, the kind of question that really separates the junior devs from the senior ones in an interview.
All right, just imagine it for a second. You're in that high-stakes coding interview. The pressure is on. We're about to walk through the exact problem that can make or break your chances. And trust me, by the end of this, you're going to know exactly how to ace it.
So yeah, think of this as your personal guide. We're not just gonna solve the producer-consumer problem, we are going to absolutely master it. We'll look at every trap, every pitfall, and of course, the best modern ways to handle it.
All right, let's get into it. The interviewer kicks things off by just laying out the basic scenario. See, before you even think about writing a single line of code, they need to know one thing. Do you really get the fundamentals?
So they're probably going to ask you to just define it. And at its heart, the producer-consumer problem is really all about coordination. You've got one process, the producer, creating data. You've got another, the consumer, using that data. But here's the catch. They both have to share this limited, fixed-size space. The real puzzle is how do you keep them from basically tripping all over each other?
And this is where a great analogy comes in, because it makes this kind of abstract software problem feel really tangible. The classic one is a factory conveyor belt, right? You've got a worker, the producer, placing items on the belt, and another worker, the consumer, taking them off. The belt itself, that's our shared buffer. And it's simple. If the belt gets full, the producer has to stop and wait. If it's empty, the consumer has to wait. And that's it. That is the whole problem, right there.
Okay, nice. You've just defined the problem perfectly. So now the interviewer kind of leans in and says, all right, show me the code. This is the moment. They want to see if you can build a really solid, robust solution from the ground up using the classic tools of the trade.
And to do this, you're going to need two key tools in your toolbox: wait and notifyAll. Think of wait as basically telling a thread, hey, you can't go any further right now, so just go to sleep. Don't waste CPU cycles. And notifyAll is the exact opposite. It's like the shift manager yelling, all right, everybody wake up. Something's changed, so check again and see if you can get back to work.
And this is basically the anatomy of a correct solution. It's got 4 essential parts. First, you need a synchronized block. That's your lock, making sure only one thread can mess with a buffer at a time. Then, inside that block, you need a while loop. And I mean a while loop, not an if. That's super important. We'll get to why later. This loop keeps checking the buffer's state. If things aren't right, you call wait. And then finally, once you've added or removed an item, you call notifyAll to let any sleeping threads know it's time to wake up.
Okay, so this is where the interview starts to get really tricky. You've written the code. It looks great. But now the interviewer throws you a curveball. They describe a buggy system, and they're not just testing your book smarts anymore. They're testing your debugging instincts. Can you spot those super subtle errors that can bring an entire system crashing down?
And they'll give you a scenario just like this. Now listen closely, because the key phrases are hangs sometimes and only under high load. That's a massive clue, right? It's telling you this isn't some simple, obvious bug. This is a concurrency issue. It's a really subtle flaw in how the threads are being managed.
Okay, so remember when I said while, not if? This is trap number 1. Here's the deal. Sometimes a thread can just wake up for no good reason. It's a weird thing called a spurious wake-up. Now, if you used an if statement, that thread wakes up, thinks, okay, I'm good to go, and just barrels ahead, even when it shouldn't. But a while loop? It's smarter. It forces the thread to wake up and immediately recheck the condition. That's what makes your code robust against these bizarre little edge cases.
And trap number 2, this is almost certainly the culprit behind that system hang. It's using notify instead of notifyAll. See, notify wakes up just one single arbitrary thread. So let's play this out. Imagine the buffer is totally full, and you've got a bunch of producers waiting. A consumer finally comes along, takes an item, and calls notify. But what if? What if the thread it wakes up is another producer? Well, that producer looks at the buffer, sees it's still full, and just goes right back to sleep. Meanwhile, the poor consumer who actually could do something is still sleeping. And just like that, your system is deadlocked. notifyAll avoids this whole mess by waking up everybody. It guarantees the right thread will eventually get a chance to run.
Okay, the interviewer is impressed. You've totally nailed the bugs. But they're not done. Now comes the real-world stress test. The system is deadlocked in production. Right now. How do you figure out what's wrong? They want to see if you can think like a real engineer who's on call at 3 a.m.
And this is where you really show your senior level thinking. You don't panic, you don't guess, you have a process. Step 1, you capture a thread dump. It's basically a snapshot of what every single thread is doing at that exact moment in time. Step 2, you comb through that dump, looking for any threads that are stuck in the waiting state. And step 3, you diagnose the problem. You figure out why they're waiting, and you confirm that absolutely no other thread is in a position to ever notify them. That's your proof.
Man, you've navigated every single trap they've thrown at you. Now comes the final question. This is the one that separates someone who just memorized the solution from a truly pragmatic engineer. The interviewer looks at you and asks, "So, knowing everything we just discussed, would you actually build it this way in a real project today?"
And your answer should be a quick, confident no. Absolutely not. Look, you've just proven that you can do it the hard way, right? That you understand the low-level mechanics. That was the whole point of the exercise. But now, you're about to show them you know a much better, much safer way.
This is when you bring up the modern, professional move. You use Java's built-in BlockingQueue. It's a class that was literally designed to solve this exact problem. It handles all that tricky locking, waiting, and notifying stuff for you under the hood. The result? It's thread safe by design. Your code becomes incredibly clean and simple, and most importantly, it pretty much eliminates the risk of those nasty, subtle deadlocks we've been talking about. It is, without a doubt, the right tool for the job.
So, you've aced the technical part. You've aced the debugging. You've aced the modern design. But there's one last thing, the grand finale. The why question that proves you don't just know the answers, you have a deep, fundamental understanding of the whole topic.
And believe me, this is their favorite final question for a reason. It's basically an open invitation for you to summarize everything, all the tricky parts, all the traps we just walked through. This is your moment to deliver that knockout punch and leave an incredible, lasting impression.
And that right there, that is the perfect, concise answer. It shows that you get it. The problem isn't just about writing a few lines of code, it's about managing immense complexity. You're pointing out that one tiny mistake, using an if instead of a while, or notify instead of notifyAll, can lead to these catastrophic bugs that are just a nightmare to track down. And your answer perfectly explains why tools like BlockingQueue even exist in the first place. They were built to handle that complexity for us. And with an answer like that, you haven't just passed the interview, you've absolutely...
Welcome to The Explainer, where we're going to dive in to one of the most maddening problems in software development, the moment your application just freezes. We're going on a hunt for the silent killers in Java multithreading that are really responsible for this. So let's kick things off with a mystery that I'm pretty sure you've all encountered. Your application just stops. It hasn't crashed, your CPU is basically asleep, but nothing. It's completely unresponsive. So what on earth is going on here? To get to the bottom of this, we've got to understand the three main villains of the concurrency world. So here's our plan. First, we'll introduce the culprits. Then we're going to unmask each one: Deadlock, Livelock, and Starvation. After that, we'll build a playbook to beat them, and then finally, we'll make sure you can ace any test on this stuff. Okay, let's get into it. Our targets are Deadlock, Livelock, and Starvation. You know, these three are the sneaky culprits that can quietly bring even the most robust multi-threaded application to a grinding halt. Just understanding them is really the first big step to writing code that doesn't break under pressure. First up on our most wanted list is the most famous of the bunch, Deadlock. The best way to think about it is like the worst traffic gridlock imaginable for your threads. It's a situation where everyone is stuck waiting for everyone else and absolutely no one can move. So what does that really mean? Well, a deadlock is a permanent standstill. Your threads are still alive, they haven't crashed or anything, but they are blocked forever. And that's why your application is totally frozen, completely unable to make any progress. And this right here shows you the classic trap perfectly. Just look at that cycle. You've got thread A, it grabs lock 1, and then it waits for lock 2. But at the exact same time, thread B has grabbed lock 2 and is now waiting for lock 1. It is a perfect catch-22. Neither one is going to give up its resource, and that creates a circular wait that leaves them stuck. For good. Now, here's what's so interesting about this. A deadlock can only happen if all 4 of these conditions, what we call the Kaufman conditions, are met at the exact same moment. And you know what? That's the secret to defeating it. You don't have to solve all 4 of these problems. If you can just break one of these conditions in your code, you stop the deadlock from ever happening in the first place. So, how do we actually break one of those conditions? Well, to prevent that circular wait condition, for instance, you can just enforce a strict lock ordering. That means all threads have to get their locks in the exact same sequence every single time. Or an even simpler fix is just to use timeouts, so a thread will eventually give up waiting after a little while. All right, on to our next villain, Livelock. Now this one is way sneakier than Deadlock. And why is that? Because your application looks busy. Your CPU usage could be totally maxed out, but just like a car spinning its wheels in the mud, it is making zero progress. The key difference, as you can see right here, is the state of the threads. With Deadlock, they're blocked. With Livelock, they're actually active and running. They're constantly trying to do something, failing, and then immediately trying again, all while being too polite to just grab what they need. They get stuck in this endless cycle of failure. This is hands down my favorite way to think about it. It's like two super polite people stuck in a hallway. One person steps aside to let the other pass, but the other person does the exact same thing at the exact same time. So they just keep mirroring each other's moves, endlessly yielding but never, ever getting past each other. They're active, for sure, but they are going nowhere. This table is basically your diagnostic cheat sheet. If your app is frozen solid and your CPU is just sitting there doing nothing, you should immediately think deadlock, your threads are blocked. But if the app is unresponsive and your CPU fan is screaming at 100%, you've probably got a Livelock, with threads stuck in a runnable state, just burning up cycles for nothing. So how do you break out of this frantic dance? Well, you have to introduce a little bit of chaos, a little randomness. So instead of having your threads immediately retry an action, you make them wait for a small, random amount of time. That little bit of unpredictability is usually enough to break the symmetry, so one thread can finally get through and make some progress. And that brings us to our final villain, Starvation. Now this one is probably the most subtle of the three. It's not about threads being stuck or spinning in circles. It's about a thread being consistently and unfairly ignored, just left waiting for resources that it never, ever gets. What this really means is you've got a thread that's ready and able to do its job, but it's just perpetually denied the chance to run. And why? Because other more greedy or maybe higher priority threads keep jumping ahead in the line, hogging all the CPU time, and leaving our poor thread to starve. A classic cause of this is misusing thread priorities. If you set one thread to the absolute highest priority and another to the lowest, the system scheduler might favor that high priority thread so much that the low priority one pretty much never gets a chance to run. It's effectively being starved of any CPU time. Now, the key difference to remember is this. Deadlock is caused by a fatal circular dependency, right? But starvation is fundamentally a problem of unfairness. The good news is that unlike a deadlock, recovery is actually possible. If those greedy threads ever finish their work, the starved thread might finally get a turn. But it's still a huge red flag that your design is flawed. So the way you fight this is by enforcing fairness right in your design. For example, in Java, you can use something called a fair lock. All this does is grant access to threads in the exact order that they asked for it. Strictly first come, first served. It's basically like setting up a proper digital queue that prevents anyone from cutting in line. Okay, so we've unmasked all three of our villains. Now it's time to build our defense. Let's put together a playbook of strategies to keep these problems out of our applications from the very beginning. This right here is your core playbook. And these aren't complicated tricks. They're really just simple disciplines. Things like always acquiring locks in the same order to stop deadlocks, using timeouts so you can escape a potential gridlock, and using the modern Java APIs that just handle so much of this complexity for you. Following these rules can really prevent these issues before they even have a chance to start. And if you remember just one thing from this whole explainer, please make it this quote. Trying to hunt down a deadlock with a debugger is an absolute nightmare. The only real way to defend against it is to design your locking strategy carefully from the very beginning. It is a design problem, not some simple bug you can just patch up later. And finally, let's make sure you can prove you've actually mastered these concepts, whether that's in a tough technical interview or when you're architecting your next big system. Knowing the theory is one thing, but being able to articulate it correctly is what really sets you apart. Okay, please be ready for these common interview traps. A deadlock is not an infinite loop. The threads are blocked, they're not looping. A live lock is not a deadlock. the threads are active and spinning, not blocked. And remember, thread priority is just a polite suggestion to the operating system scheduler, not a guarantee of execution order. Nailing these distinctions really shows you know your stuff. So let's wrap this all up with this one key idea. Deadlock blocks, Livelock spins, and Starvation denies. All three of them are simply symptoms of a poor concurrency design. They aren't just abstract academic problems. They are real-world failures that you can and should prevent. And by understanding their causes and applying the right strategies, you can build applications that are robust, efficient, and
All right, let's dive straight into a classic concurrency puzzle, one that trips up even really experienced Java developers. We're going to unravel the whole mystery of the volatile keyword. And trust me, by the end of this, you'll get not just what it does, but why it's so incredibly important. So take a look at this code. On the surface, it seems totally straightforward. You've got a while loop that should run for about a second and then stop. But here's the weird part. A lot of the time, it just doesn't. It gets stuck in an infinite loop. What is going on here? Okay, here's the setup. We have one thread that's just looping, checking a running flag over and over. Then our main thread comes along and sets that same flag to false. Simple enough, right? The problem is the looping thread might just never see that change. So what's the fix? Well, the fix is surprisingly simple. It's not some complicated lock or a total redesign of the code. Nope, it's a single keyword. That's it. Let's see it in action. This right here, this is our problem line. Without any special instructions, the Java virtual machine is free to make an optimization. It lets the looping thread cache the running flag's value. To be fast, it just keeps reading its local copy and never bothers to check if the original has changed. And boom! By simply adding the word volatile, the problem is solved. It works exactly as you'd expect every single time. But, this isn't magic. It's all about how computer memory actually works. To really understand how that one little word fixed our bug, we have to talk about the official rulebook for threads in Java. It's called the Java Memory Model, or JMM for short. So why do we even need a JMM? Well, it's because modern hardware is all about speed. It has things like CPU caches, and it reorders instructions to be more efficient. That's great for a single thread, but it can create absolute chaos for multi-threaded code. The JMM gives us a set of consistent rules that all threads have to follow. Here's the key concept you need to get. Think of a central whiteboard. That's your main memory, shared by all threads. Now, each thread gets its own private notepad. That's its working memory, or cache. A thread copies variables from the whiteboard to its notepad to work on them. Our original problem? The looping thread just kept staring at its own notepad and never looked up to see that someone had updated the main whiteboard. And this is precisely what volatile does. It's a command. It tells the threads, hey, for this variable, forget your private notepad. Every single time you read it or write to it, you have to go directly to the main whiteboard. This guarantees visibility. It ensures everyone is looking at the same up-to-date information. Now, it's super tempting to think of volatile as this magic wand you can wave to fix any concurrency problem, but that is a really dangerous trap. It solves one very specific problem, and that's it. So let's bust a few myths and talk about what it can't do. Okay, if you're ever in a technical interview, this is the line to remember. Say it with me. Volatile fixes visibility, not race conditions. It guarantees you will see the latest value, but it does absolutely nothing to make sure a sequence of operations is safe from interruption. For example, take a simple operation like count++. It looks like one thing, right? One step. But it's a lie. Under the hood, it's actually 3 separate steps. Read the value, add 1 to it, and then write the new value back. Even if count is volatile, another thread can sneak in between those steps and you can end up losing updates. This is not an atomic operation. So, let's make this crystal clear. With volatile, what do you get? You get 100% visibility, guaranteed. What don't you get? You get 0% atomicity for those compound read, modify, write operations. And this table just lays it all out. It really shows why volatile can't replace a synchronized block. See, synchronized is the whole shebang. It gives you visibility, sure, but it also gives you atomicity for entire blocks of code and mutual exclusion, meaning only one thread can be in that block at a time. Volatile is a much lighter, more specialized tool. All right, so we've covered the what and the whatnot. Now let's get to the core principle that really governs all of this. It's a concept from the Java memory model called the happens before relationship. It's the formal framework for all this stuff.
Think of happens before as a contract, a formal promise from the JMM. If the rules say that action A happens before action B, it's a guarantee that everything action A did, especially its memory writes, will be perfectly visible to the thread that's about to perform action B. No guesswork involved.
Now, the JMM has a bunch of these rules for things like locks and starting threads. But check this out. The one that matters to us right now is the volatile variable rule. It states that a write to a volatile variable happens before every subsequent read of that same variable. That's it. That's the formal guarantee, the why behind our fix. It's the rule that makes the magic work.
Okay, we've gone through the problem, the fix, the deep theory, and the limitations. Let's put this all together into a practical toolkit that you can actually use in your code and, of course, ace that next interview question.
So here's the bottom line. Use volatile for simple status flags. Think things like running is shut down or is ready. It's perfect when one thread writes to the flag and other threads just read it to know what to do. But the second a variable's new value depends on its old value, like with a counter, volatile is the wrong tool for the job. You need something stronger.
And here it is, your killer interview line. If you want to show that you don't just know the what, but the why, this statement is gold. It connects the Java memory model, volatile, the happens before relationship, and the core philosophy of writing correct, reliable, concurrent code. It shows you get the big picture.
So, hopefully this gives you the tools to not only fix bugs, but to start seeing your code through a new lens, the lens of the Java memory model. Concurrency isn't just random bugs, it's a system with rules. And now that you know the rules, the real question is, what puzzles are waiting to be found in your own code?
All right, if you're a Java developer, you already know that concurrency questions can absolutely make or break a technical interview. So today, we're going to deep dive into one of the most important tools you have for multi-threading, Java's atomic variables. Let's get right into it.
Just think about that for a second. You've got 1,000 threads all hammering away at the same single number, trying to increment it. I mean, without the right kind of protection, you are walking straight into a classic race condition. The final count, it's going to be a total mess. And this right here is the exact problem that atomic variables were built to solve. And they do it with some serious elegance and efficiency.
So here's the game plan. We're going to start with that core problem, then introduce the beautiful lock-free solution. After that, we'll pull back the curtain and reveal the secret sauce that makes it all work. Then we'll expose a really critical flaw that you absolutely have to know for your interviews. And finally, we'll stage a showdown to help you figure out exactly when to use which tool.
Okay, so that shared counter we were just talking about, that's a textbook race condition. You have all these threads racing to read the value, add one to it, and write it back. And in the process, they just stomp all over each other's work. Now, the traditional way to fix this is using the synchronized keyword, which basically puts a big lock on your code. And yeah, it works, but it can be kind of heavy. It forces all the other threads to just stand there and wait in line, and that can really slow your application down. But what if? What if you could get all that thread safety without making your threads wait? Well, that's exactly where the java.util.concurrent.atomic package comes in. You can think of it as Java's modern, super sleek alternative to those explicit locks, at least for simple operations. It gives you a way to perform actions on a single variable that are guaranteed to be atomic, completely indivisible.
Now here's the definition you'll want to remember for an interview, and the two key phrases you need to burn into your memory are lock-free and low-level CPU instructions. See, this isn't some kind of magic that's just happening inside the Java virtual machine. Nope. This is Java reaching down and using powerful, lightning-fast features that are built right into the hardware, right into the CPU itself. That's where the performance comes from.
And this whole concept isn't just for integers either. It works for longs, for booleans, and even for any generic object you want using atomic reference. Oh, and see that last one on the list, atomic stamped reference? Keep that one in the back of your mind. It solves a really subtle but really dangerous bug that we're going to talk about in just a bit. And just look at how clean the code is. You just create a new atomic integer, and then you call a method like increment and get. And that's it. That one little method call is guaranteed to be thread safe. There's no bulky synchronized block, no extra boilerplate, just a simple, direct, atomic operation. It's beautiful.
So you're probably wondering, how in the world does Java pull this off without using locks? Well, the magic behind it all is an operation called compare and swap, or CAS for short. This is the engine that drives the entire atomic library, And really understanding how this works, well, that's what separates a pretty good interview answer from a truly great one.
So compare and swap, or CAS, is an instruction that happens at the hardware level. It basically says this: hey, I expect the current value in memory to be X. If it is still X, go ahead and update it to Y. But if it's not X anymore, then just do nothing and let me know that I failed. And the crucial part is that this whole check and update thing happens is one single indivisible operation. It's kind of like trying to save a document on a shared drive. You can only save your changes if nobody else has saved a new version since you first opened it.
So let's see how Java uses this. When your code calls something like increment and get, it's not just one single CAS operation. It's actually a loop. Your thread reads the current value, it figures out the new value, and then it uses CAS to try to make the update. Now, if some other thread snuck in and changed the value first, the CAS operation fails. But here's the cool part. Instead of going to sleep, the thread just says, whoops, okay, I'll try again. It just goes back to step 1, reads the new value, and repeats the whole process. That's why we call this a non-blocking or lock-free approach.
And this slide just perfectly illustrates the two outcomes. On the left, you've got the happy path. Thread 1 expects the value to be 5. It is 5, so it updates to 6. Success. But look at the right. This is where things get interesting. Thread 1 expects 5, but before it can make its move, Thread 2 jumps in and changes the value to 8. So when Thread 1's CAS operation finally runs, it sees the current value is 8, which does not equal the 5 it expected. So the update is rejected, and Thread 1 has no choice but to go back and start all over again.
Okay, so at this point, compare and swap seems pretty foolproof, right? It's fast, it's lock-free, what's not to love? Well, it has one very subtle but very critical weakness that interviewers just love to ask about. It's called the ABA problem. And if you don't know what it is, you could accidentally introduce some really nasty bugs into your code. Let's just walk through this timeline together. At time 1, Thread 1 reads a value, we'll call it A. But before it can do anything with it, it gets paused. While it's sleeping, Thread 2 swoops in, changes the value from A to B, does some work, and then changes it right back to A. Now Thread 1 wakes up, it goes to do its cast check, it asks, is the current value the A I expected? And the answer is yes, the check passes. But Thread 1 has absolutely no idea that the state was secretly modified and then changed back. It's been completely fooled.
So how on earth do we fix this? Well, remember that special class I told you to keep in mind? This is its moment to shine. This is where atomic stamped reference comes to the rescue. It doesn't just store a value, it pairs that value with a version number, or what we call a stamp. Every single time the value gets updated, the stamp gets incremented too. So now the CAS operation checks both the value and the stamp. And that, my friends, completely solves the ABA problem.
All right, we've gotten deep into the weeds of how this stuff works. Now it's time for the practical payoff. Because in an interview, you are almost guaranteed to be asked this question. When should you use an atomic variable? And when should you just stick with good old synchronized? Knowing the trade-offs here is absolutely essential.
This table really lays it all out. Atomics are lock-free and non-blocking, right? And that gives them a massive performance edge when there isn't a ton of contention. But, and this is a big but, their scope is limited to just a single variable. On the other hand, synchronized is lock-based. It can cause threads to block and wait, but it's way more flexible. You can use it to protect really complex operations that involve changing multiple variables all at once. So the key takeaway is this. Atomics are a specialized tool for high-speed, single-variable updates. They are not a silver bullet for every concurrency problem you'll face.
Now, if you need one perfect, concise sentence to use in your interview, this is it right here. It shows that you understand the main benefit, you're avoiding blocking, but you also get the primary drawback, which is that under really heavy load, all those constant CAS retries can actually start to hurt performance because the CPUs are just spinning and spinning, trying again and again.
And just to make sure you really sound like a seasoned pro, here are the traps you need to avoid. Please, don't ever say that atomics replace synchronized. They complement each other. Don't claim they're always faster because of that high contention issue we just talked about. And most importantly, never ever suggest using an atomic variable for an operation that needs to atomically update multiple variables at once. That is a job for locks, period. So, to wrap it all up, here is your strong, confident closing statement. This one sentence summarizes everything we've covered. The mechanism, which is CAS, the primary benefit, which is scalability, and the critical things to watch out for, like the ABA problem and their limited scope. Saying something like this shows a really deep and nuanced understanding of the whole topic. And that brings us to the final question, and this one's for you to think about. The next time you're building something and you're faced with a shared variable in a multi-threaded world, which tool are you going to reach for first? And even more importantly, why?
Knowing the answer to that is what truly makes you a master of concurrency. Thanks so much for joining me.
All right, let's talk Java interviews. You know concurrency questions are going to pop up, right? They're a big deal. And one of the classics is the difference between the synchronized keyword and the lock framework. Nailing this down isn't just about acing the interview, though. It's about writing way better, more solid concurrent code in the real world. So let's kick things off with the big question every pro developer has to ask themselves. When you're dealing with threads and shared data, are you actually grabbing the right tool from your toolkit? Because believe me, the choice you make here, it has huge consequences for performance, for flexibility, and just how tough your application is. Okay, so let's cut right to the chase. The interviewer hits you with a question, what's the core difference? Here's your go-to high-level answer. Think of Synchronized as the simple, safe, built-in option. But Lock, that's the flexible, powerful API. It's like upgrading from a hand drill to a full-on power tool. And that one simple distinction, it really sets the stage for everything we're about to cover. So here's how we're going to break it down. First, we'll look at the standard tool, Synchronized. Then we'll level up to the Pro Toolkit with Lock. We'll do a deep dive on its main workhorse, reentrant lock, check out a specialty tool called read-write lock, and wrap it all up with the perfect closing statement for your next interview. All right, first up, Synchronized. This is the standard tool that's in every Java developer's toolbox from day one. You know, its biggest selling point so that it's super simple and safe. But, and this is a big but, that simplicity comes at a cost. It's pretty limited. So, what exactly is it? Synchronized is a keyword. It's baked right into the Java language. When you slap it on a method or a block of code, the JVM takes care of all the heavy lifting for you. Getting the lock is implicit. It just happens automatically when a thread enters that code. And this is crucial, releasing the lock is also automatic. You literally can't forget to release it, which is a huge safety net. Okay, now let's switch gears and look at the lock interface. This is where things get interesting. This is where you get all that fine-grained control that Synchronized it just can't give you. You're basically switching from automatic to manual transmission, and you get a whole bunch of cool new features in the process. Like, for example, what if a thread is just sitting there waiting for a lock, and you need to tell it, hey, stop waiting, go do something else? Well, with the lock framework, you can totally do that. It's called interruptible waiting. And what about fairness? You know, making sure everyone gets a turn. Have you ever wanted to make sure that the thread that's been patiently waiting the longest is the next one to get the lock? Yep, the Lock API lets you do that. You can actually create fair locks. Okay, this table really puts it all side by side. Synchronized, that's a language keyword. Lock, it's an API. Getting and releasing the lock is all automatic with Synchronized, but with Lock, you have to do it yourself. It's explicit and manual. And now for the cool features. Interrupts? Nope for Synchronized. A way to try for a lock without getting stuck? That's try lock. And nope, Synchronized doesn't have it. Fairness control? Not a chance. Lock, on the other hand, gives you a big yes to all three. This is where you really see the upgrade. All right, let's dive deeper into the most common implementation of lock you're going to see out in the wild, reentrant lock. Seriously, think of this as your main workhorse. When you decide you need a lock, this is probably the one you'll grab. So a reentrant lock is what we call a mutual exclusion lock, but it has this really cool property called reentrancy. What that means is if a thread already has the lock, it can ask for it again and it won't block itself. It just gets it again. Why does this matter? Well, it's essential for stuff like recursive methods or when one locked method calls another locked method. It stops the thread from deadlocking with itself, which would be bad. So just to recap, reentrant lock packs a lot of power. You get that reentrancy we just talked about, but you also get to choose a fairness policy, you get that interruptible locking, and you even get a version of try lock where you can say, hey, try for this long and then just give up. It's just a way more flexible and powerful tool. Okay, let's zoom in on that fairness policy for a sec. A fair lock is kind of like a polite line at the bank. It's first in, first out. This is great because it means no thread gets left behind or starved. Now, the default is actually an unfair lock. It makes zero guarantees about order. A new thread might just barge in and grab the lock, cutting in line. This can actually lead to better performance, higher throughput, but it comes with the risk that some threads might never get their turn. And this brings us to a fantastic, punchy line you can use in an interview. Just say this, fair locks trade performance for predictability. Boom. It's short, it's accurate, and it shows you totally get the trade-off. Another one of those killer features is interruptible locking. When you call lock interruptibly, you're basically telling your thread, Go ahead and wait for that lock. But hey, if someone interrupts you while you're waiting, just stop waiting and deal with the interruption. A thread that's stuck waiting on a synchronized block, it can't do that. It's just stuck indefinitely. So why should you care? Why does this even matter? Well, it's absolutely essential for building systems that are responsive. Think about it. Graceful shutdowns, canceling a task that's taking too long. You need a way to tell those waiting threads to just stop and clean up. Interruptibility is how you make that happen. Okay, time for a specialty tool. Imagine you have some data that gets read, like 1,000,000 times, but only gets written to once in a while. If you used a standard lock, you'd create a huge bottleneck. That's where read-write-lock comes in. It's designed for exactly this scenario.
And let me tell you, the performance difference can be absolutely massive. In that situation with tons of readers and just a few writers, a normal synchronized lock or even a re-entrant lock forces everyone to stand in a single line. It creates a ton of contention. But a read-write lock, it's like opening up a bunch of express lanes for all the readers. They can all go at the same time, leading to this huge boost in performance. The magic behind it is actually pretty simple. It just keeps two separate locks, one for reading and one for writing. The genius part is that tons of threads can hold the read lock at the same time as long as nobody has the write lock. The write lock, though, is totally exclusive, only one writer at a time. And that separation is the whole secret to its amazing performance.
So when do you pull this special tool out of your bag? The checklist is pretty simple, actually. You use it when you have way more reads than writes, when the data doesn't change very often, and when any write operation has to be totally exclusive. Think about things like caches, or configuration data that gets loaded at startup, or any kind of in-memory lookup table. Perfect use cases. Okay, let's wrap this up by talking about the right mindset. How to use these tools correctly. You know the saying, with great power comes great responsibility? Well, it's true here. You've got to be aware of the common traps. We'll go over those, and then I'll give you that killer closing statement for your interview. Okay, listen up, because this is rule number 1. It is absolutely non-negotiable. Since you're the one who manually grabs the lock, you and only you are responsible for releasing it. If some exception happens inside your protected code, and you haven't put your unlock call in a finally block, guess what? That lock is held forever. Deadlock City. So always, and I mean always, use a try finally block with lock. The second big trap is falling in love with a new shiny toy and thinking lock is always better. It's not. For really simple cases where you don't expect a lot of contention, synchronized is often just fine. It's cleaner, it's less code, and it's harder to mess up. It all comes back to our main theme, right? Use the right tool for the job.
And that brings us to the grand finale. Here is a really strong, confident way to wrap up your answer in an interview. You can say something just like this. While synchronized is great for simple cases, the lock framework provides far more advanced concurrency control. It enables critical features like fairness policies, interruptible locks, and fine-grained control like read-write lock. These are all essential for building truly scalable and responsive concurrent systems. See? A statement like that shows you don't just know what the tools are, you understand why they exist and when to use them. And that, right there, is the real key.
All right, let's talk about one of the absolute cornerstones of modern Java development, the executor framework. You know, if you've ever dealt with multi-threaded code, it can feel like you're walking through a minefield. So how do we handle concurrency and manage threads without, bringing our entire application crashing down? Well, that's exactly what we're going to get into.
So let's start with this single line of code. I mean, almost every single one of us has written this at some point. It looks so harmless, right? You've got a task, you wrap it in a new thread, you hit start, boom, done. But in a real, live production system under any kind of serious load, this line of code is a ticking time bomb. Let's dig into exactly why.
Okay, so here's the deal. Creating threads manually is just incredibly expensive, and honestly, pretty dangerous. First off, every single thread you spin up eats a pretty big chunk of memory for its stack. Then there's the overhead, the time it takes the operating system to actually create and then tear down that thread. It all adds up and slows you down. But the real killer, the thing that will get you a call at 3 a.m., is that there's no upper limit. You get a sudden spike in traffic, and your app just keeps creating threads, hundreds, maybe thousands, until you get what's called a thread explosion. And that almost always ends with a fatal out-of-memory error. Game over.
And that idea right there is the solution. It's a total shift in mindset. We have to stop thinking about one new thread for one new task. Instead, we need to think about having a managed pool of worker threads that are just ready and waiting to pick up work. It's about moving from total chaos, unbounded creation, to a system of controlled, predictable concurrency. And this is exactly where the executor framework comes into play. It's this beautiful abstraction that lets you separate the what from the how. Your code just says, hey, here's a task I need to run. You submit it, and you're done. The framework takes care of all the messy details in the background, reusing threads, queuing tasks, managing the whole lifecycle. You get to focus on your business logic, not on the plumbing of thread management.
Now, when you dive in, you're going to see two main interfaces, Executor and ExecutorService. Think of Executor as the super simple base. It just has one method, execute, which is basically fire and forget. But for any real work, you're going to be using ExecutorService. It gives you all the crucial stuff you need for production, like being able to shut the pool down cleanly, and really importantly, a submit method that gives you back a future object. That future is your ticket to getting a result back from your asynchronous task.
Okay, so we know we want to use an ExecutorService. The next question is, which one? Luckily, Java gives us a really handy factory class called executors with a bunch of pre-configured options. It's all about picking the right tool for the job, so let's walk through the big ones. First up, we've got the workhorse of the bunch, the fixed thread pool. It does exactly what it says on the tin. You tell it you want, say, 10 threads, and that's what you get. No more, no less. What's great about this one is that it's super predictable. If all your threads are busy working, any new tasks that come in just line up in a queue and wait their turn. This makes it absolutely perfect for things that have a pretty steady workload, like a typical web server. And here's a pro tip. For tasks that are heavy on CPU calculations, you usually want the number of threads to be pretty close to the number of CPU cores you have. That way you avoid wasting time with excessive context switching. All right, next we have the cached thread pool. This one is the complete opposite of the fixed pool. It's all about being dynamic and flexible. It'll create new threads on the fly whenever it needs them. So it's designed for situations where you have a whole bunch of short, quick tasks. It's smart enough to reuse threads that just finished their work, but if every thread is busy, it has no problem just creating a new one. But, and you can see that big warning there, because it can create an unbounded number of threads, it has the exact same thread explosion problem we talked about at the beginning. Using this on a server is a classic interview trap and a recipe for disaster in production. Then we have the simplest one of all, the single thread executor. And yeah, you guessed it. This one uses just a single worker thread to get everything done. Now you might be thinking, why on earth would I want that? Well, the killer feature here is that it gives you an absolute guarantee that your tasks will run one after the other in the exact order you submitted them. This is a lifesaver for any task that absolutely must not run at the same time as another one. Things like writing to a log file or maybe processing events in a specific sequence where order matters. And last but not least, we have the scheduled thread pool. This one is all about time. It's designed for tasks that you need to run at some point in the future. This is your go-to for any kind of background scheduling you can think of. You can tell it, hey, run this task for me in 5 seconds, or run this cleanup job every hour on the hour. You can think of it as having a little cron system built right into your Java app. It's perfect for things like periodic health checks, pulling an external service, or running daily reports. So we've seen the what, these different prepackaged pools, but to really master this stuff, we need to understand the how. Because behind the scenes, all of those factory methods are just creating and configuring one super powerful class, the thread pool executor. So let's pop the hood and see how this engine really works. This is the secret sauce. This is the logic that runs every single time you submit a task. First, the executor asks, do I have any of my core threads free? If the answer is yes, great, that thread gets the task. If all the core threads are busy, it asks question 2, is there room in the work queue? If yes, the task gets added to the queue to wait. But what if the queue is also full? Then it asks a third question, can I create a new temporary thread without going over my maximum pool size? If it can, it does. And only if the answer to all of those is no, core threads busy, queue full, and max threads reached, only then does it move to the final step, rejecting the task. And that queue we just mentioned? It's a hugely critical piece of this puzzle. You generally want a bounded queue, like an array blocking queue, because it has a fixed size.
That forces your system to confront the reality of being overloaded. An unbounded queue like linked BlockingQueue is dangerous. It just keeps accepting tasks, growing and growing, silently hiding the fact that your system can't keep up until it finally blows up with an out-of-memory error.
So that brings us to that final, drastic step in the decision flow. What happens when the system is completely overwhelmed? All threads are busy, the queue is totally full. This is where the rejection policy kicks in.
Now, the default policy is called abort policy, and it just throws an exception. It fails fast, which is at least honest. The other standard ones, though, they're usually a bad idea. Discard policy just silently drops the task. Poof, gone. That's potential data loss. And discard oldest policy is even weirder. It throws away the task that's been waiting the longest to make room for the new one. It's just really unpredictable. Surely there has to be a better way.
And there is. This right here is a huge topic in senior Java interviews, and for a very good reason. It's called the caller runs policy. This policy is absolutely brilliant. Instead of throwing an exception or just dropping the work, it does something really clever. It basically says to the thread that tried to submit the task, hey, we're totally slammed right now. You do the work yourself. This creates what's called back pressure. The thread that was busy submitting new tasks is now stuck doing the work itself, which means it can't submit any more tasks for a while. It naturally and gracefully slows down the producer to match the speed of the consumer. It creates a stable, self-regulating system.
Okay, so let's wrap this all up with a quick checklist of the big mistakes, the traps you want to avoid. First, never ever use a cached thread pool in a server application. Second, always favor bounded queues over unbounded ones. You want to know when you're overloaded. Third, and this is a common beginner mistake, always remember to shut down your executor service, or your application will never exit cleanly. And finally, don't just use those executors factory methods blindly. Understand what's happening underneath so you can tune the thread pool executor for your specific needs. And really, that's the whole story right there. The executor framework gives you this wonderful, high-level abstraction that makes concurrency so much easier. But the thread pool executor is what gives you that deep, fine-grained control over your resources, how your system behaves under pressure, and how resilient it is. And getting that configuration right, well, it's not just some academic thing. It is absolutely fundamental to building robust, scalable, production-ready applications in Java.
All right, let's talk Java. If you're getting ready for a tech interview or you're just trying to squeeze every last drop of performance out of your code, you are in the exact right place. Today, we're diving into one of the most powerful concurrency tools in the JVM, the fork/join framework and its super convenient sidekick, parallel streams.
So, let's kick things off with a simple question. You've got this awesome multi-core processor sitting in your machine, right? But is your code actually using all of them? Most of the time, a standard application just runs on one core, leaving all that other horsepower completely unused. It's kind of like having an 8-lane superhighway but forcing all the cars into a single lane. This is the exact problem that the fork-join framework was built to fix.
And that, right there, is what we call the multi-core CPU problem. We have all this amazing potential just sitting there in our hardware. So the real challenge is, how do we smartly break up our work and spread it across all those cores to get things done way, way faster?
And that leads us to Java's really elegant solution. The fork/join framework is all about that classic divide and conquer strategy, but it's been totally supercharged for the hardware we have today.
Okay, here's the definition you're going to want to remember for any interview. It's a specialized framework, and that word is key. It came out way back in Java 7, and it's specifically for tasks you can break down over and over again. And the most crucial part, it's optimized for CPU-intensive work. We're talking heavy-duty calculations, not sitting around waiting for a database to respond.
The strategy is actually really simple when you look at it. It's just 3 steps. First, you take a big, complex task and you split it into smaller, bite-sized pieces. Next, you execute all those little pieces at the same time, in parallel, on different CPU cores. And finally, you take all those individual answers and combine them back together to get your one final result. Simple, right?
So let's get into the nitty-gritty of how the code actually works. Imagine you're splitting a job in 2. When your code says left.fork, the thread you're on is basically saying, hey, some other worker thread, go start on the left half. I'm not going to wait for you. That happens asynchronously. Then your original thread immediately gets to work on the right half by calling write.compute. That's synchronous. It does the work itself. Once it's done, it calls left.join, which is its way of saying, okay, I'm finished. Now I'll just wait here until that other thread is done with the left half, and then we can put our results together. That whole fork, compute, join dance is the absolute heart of how this thing works.
Now, this all sounds pretty cool,
But what makes the fork/join framework so much more efficient than, say, a regular thread pool? Well, the answer is its secret sauce, a really clever algorithm called work stealing. And trust me, this is a huge interview topic.
So how does this work stealing thing actually work? Well, picture each worker thread with its own personal to-do list. Technically, it's a DQ, which just means it can pull tasks from the front or the back. A thread normally just chugs along, working on tasks from its own list. But here's the magic. If a thread finishes all its work and has nothing to do, it doesn't just go on a coffee break. Nope. An idle thread will actually go look at another thread's to-do list and steal a task to work on. This is brilliant because it keeps all the CPU cores busy all the time. It's a self-balancing system.
And hey, if you really want to nail it in an interview, here's your golden one-liner. Just say this: work stealing is all about maximizing CPU utilization by dynamically moving work to where there's free capacity. It's just an incredibly efficient way to handle load balancing.
Okay, so fork/join is clearly powerful, but let's be honest, writing those special task classes can feel a little clunky. So now let's talk about the much more common way you'll use this power: parallel streams. Think of this as the easy-to-use shortcut.
So what is a parallel stream? It's really just a regular Java stream that's been told to run its operations in parallel. But the key thing to get is that under the hood, it's using the exact same fork/join framework we just talked about. You don't have to manage any threads yourself. You just call .parallelstream, and Java handles all that complexity for you.
So the choice between a regular stream and a parallel stream really comes down to a trade-off. A sequential stream is simple, it's predictable, and there's almost no overhead. A parallel stream, on the other hand, can give you a massive performance boost, but it comes at the cost of higher coordination overhead. You're basically trading some control for a whole lot of convenience.
Okay, listen up, because this is probably the single most critical thing to understand about parallel streams. By default, all parallel streams in your entire application share one single JVM-wide thread pool. It's called the common pool. This isn't your own private pool for your task. It's global. And this has huge, huge implications, as we're about to see.
Right. Because of that shared pool, knowing when not to use these tools is maybe even more important than knowing when to use them. So let's get into the critical traps and best practices that are going to keep your apps running fast and, more importantly, stable.
So here's the bottom line. You have to use fork/join and parallel streams for the right kind of job. This table breaks it down perfectly. You want CPU-bound tasks, not I/O-bound tasks that wait for things. Your operations need to be independent, not blocking. And your code should be stateless, not messing with shared mutable data. If you block a thread in that shared common pool, you could literally starve other critical parts of your application. So the rule is simple. Fork/join is for number crunching, not for waiting. Let's be super explicit here. Just don't do it. Do not use parallel streams for tasks that involve I/O, like hitting a database or calling a REST API. Don't use them on tiny datasets either, because the overhead of splitting everything up will actually make it slower. And definitely avoid them if your code is stateful or relies on shared mutable data.
And this right here, this is a perfect example of what not to do. You've got multiple threads all trying to call add on the same non-thread safe array list at the exact same time. This is a textbook race condition. It's a complete disaster waiting to happen. You're going to get wrong answers, weird exceptions, and a really bad headache. It's a massive anti-pattern.
So if you can't use fork/join for I/O, what should you use? That's where our old friend the ExecutorService comes in. It's designed for exactly that, independent tasks that might block. Fork/join is for your recursive, CPU-heavy work. The ExecutorService is your go-to general-purpose tool for pretty much everything else, especially I/O. It's all about using the right tool for the job.
Okay, to bring it all home, let's just hammer through these common interview traps. Ready? No, going parallel is not always faster. No, parallel streams won't always make your code better. Absolutely not. It is not safe to do I/O in parallel streams. And for the last time, no, they do not get their own thread pool. They all use that one shared common pool. If you can avoid these mistakes, you're already ahead of the game.
And we'll end with this. This is your perfect polished summary for any interview or technical chat. It shows you understand the power of the framework, you get the efficiency of work stealing, you appreciate the convenience of parallel streams, but most importantly, you know about the critical danger of blocking that shared pool. So, next time you're writing code, just ask yourself, is this really a job for
Okay, let's talk about that moment in a Java interview. You know the one. The interviewer leans in and says, "So, tell me about completely future fire." And maybe you feel a little bit of a panic. Well, you're not alone. In the next few minutes, we're going to completely demystify this. We'll walk through a solid game plan that will not only help you answer the questions, but show that you really get asynchronous programming in Java. Let's get you ready to ace this. All right, here we go. The interview kicks off with that classic question. How you answer this first part is so important. A sharp, confident definition right off the bat shows you have a rock-solid foundation. And believe me, that sets a great tone for the entire rest of the interview.
So what do you say? Here's the perfect one-liner. You want to say something like, complete future, which came out in Java 8, is an abstraction for an asynchronous, non-blocking result of some computation. And the real kicker is this next part. And it lets you build these amazing async pipelines using functional-style callbacks. Hitting those key points, Java 8, async, non-blocking, and pipelines shows you don't just know what it is, but you understand why it's so powerful. Now, to really stand out, you have to tell the story of why it even exists, right? Before completable future, we had the old future interface. And honestly, it had some major problems. First off, its get method was blocking. I mean, what's the point of async if you're just going to sit there and wait? It totally defeats the purpose. Plus, you couldn't easily chain tasks together, and the exception handling was, well, not great. Completable Future came along and fixed all of that. It gave us non-blocking callbacks, this beautiful, fluent way to build pipelines, and error handling that actually works. It was a total game changer.
So here's our roadmap. We're going to start by absolutely nailing that opening question. Then we'll dive into the fun part, building async pipelines. After that, we'll tackle combining different tasks and dealing with errors when things go wrong. Then we'll shift into some pro-level knowledge that'll make you look like a senior dev. And finally, we'll wrap it all up with a powerful closing statement. So a good interviewer isn't just going to stop at the definition. They'll probably follow up with something like, okay, so how do you actually create one? Let's dig into that, because it's a fundamental piece of the puzzle.
And that follow-up question is almost always about creation. You really only need to know two main ways to start things off. First, you've got supply async. You use this when your task is going to compute something and return a value. It takes a supplier, which is just a fancy name for a function that gives you a result. Simple enough. On the other hand, you've got run async. This is for your fire and forget tasks, the ones that just do something but don't return anything. It takes a runnable, which, you guessed it, is just a task that runs. That's it.
Okay, now for the really cool part. The true magic of Complete Futurefy happens when you start chaining these asynchronous operations into a pipeline. This is where a lot of people get tripped up, so let's walk through it nice and slow. So the interviewer might throw you a curveball. They'll say, okay, you fetch a user ID, and then you need to use that ID to fetch the full user object in another async call. How do you do that? Now, your first instinct might be to use then apply. But if you do that, look what happens. You get this ugly nested thing. A complete future table inside another complete future table. It's a super common mistake, and it just makes your code a mess to work with. And here's the elegant solution. Then compose. This method was built for exactly this situation. It takes the result from the first future, feeds it into a function that creates a new future, and then, this is the magic part, it automatically flattens that nested structure for you. So instead of that messy, double-wrapped future, you just get one clean, single, completable future with your final result. Beautiful. So here it is, the one rule you need to remember. Use then apply when you're doing a simple synchronous transformation on a result, like, say, turning a string to uppercase. But you use then compose when your next step is another asynchronous task that needs the result from the first one. Getting this distinction right is probably the single biggest step to mastering complete future task. All right, let's level up. We're moving into more advanced real-world stuff now. We're going to look at how you can combine the results of totally independent tasks and, just as important, how to handle things gracefully when they inevitably go sideways. Okay, picture this. You need to get user details from one microservice and their order history from a completely different one. These two things don't depend on each other, so you can, and should, run them at the same time. This is the perfect job for then combine. It takes two futures, waits for both of them to finish, and then gives you a way to merge their results together. It's an incredibly powerful way to speed up your application by running things in parallel. Let's be real, things are gonna fail. Handling exceptions in an async pipeline is absolutely critical. You've got three main tools here. First, exceptionally. Think of this as your plan B. If an exception happens, this method catches it and lets you provide a default fallback value. Then there's handle, which is more powerful. It gets called no matter what, success or failure.
It gives you both the result and the exception, so you can decide what to do in either case. And finally, when complete. This one is for side effects, like logging. It lets you peek at the outcome, but you can't actually change it. We're in the big leagues now. If you can talk intelligently about the threading model and common mistakes, you're not just answering questions anymore. You're showing a deep, practical understanding that goes way beyond the basics. Sooner or later, you're going to get asked about that async suffix. What's the difference between then apply and then apply async? Here's the key insight. It's not about what the code does, it's about where it runs. The version without async might run your code in the same thread as the previous task. And if that's a sensitive I/O thread, you definitely don't want to block it. The async versions, however, guarantee your task gets handed off to a proper thread pool. This gives you way more control and keeps your application responsive. And this is where you can score some serious bonus points. Show them you're not just book smart, but you've been in the trenches. Talk about the common traps people fall into, like calling that blocking get.method all over the place, or that classic mistake of mixing up then apply with then compose. A big one, especially in server apps, is forgetting to provide a custom thread pool and accidentally starving the system's main thread pool. When you bring up these kinds of real-world pitfalls, it sends a clear signal. This person has actually built stuff with this. It's a huge credibility boost. Okay, time to bring it all home. After you've crushed all the detailed questions, you get a chance to tie it all together with a powerful summary. This is where you connect all the dots and leave a really strong, lasting impression. You can wrap everything up with a perfect real-world example. Just talk about modern microservices. You might need to call a user service and an order service to build a single web page. Complete Future is literally the perfect tool for this job. Why? Because it lets you do non-blocking I/O and run those calls in parallel, which is absolutely essential for building systems that are fast, scalable, and responsive. So, to wrap it all up, you can say something like this. Complete Futurefy is an essential tool for modern Java development. It enables a declarative, non-blocking, asynchronous style of programming that is perfectly suited for today's microservice architectures, where building scalable and responsive systems is the name of the game. A summary like that connects all the technical details right back to real business value. It's the perfect way to end.
And there you have it. That's our complete tour of Complete Future. By really understanding these concepts, from how you create them to the tricky parts about threading and error handling, you are more than ready to handle any interview question on this topic with total confidence. Now go out there and nail it.
Hey everyone, if you're a Java developer, you know that multithreading is one of its most powerful features, but it's also one of its most dangerous. So today we're going to do a real interview-level deep dive into a topic that is absolutely critical in modern Java, thread safety, and what is arguably its most elegant solution, immutability.
So, let's start with the absolute core of the problem we're trying to solve here. Imagine two people are trying to update a number on a whiteboard. One person reads the number 5 and wants to add 1. At the exact same time, another person also reads 5 and wants to add 1. Now, if they're not careful, they might both just erase the 5 and write 6, when the correct answer should obviously be 7. That chaos right there, that's called a race condition, and it is the absolute bane of concurrent programming.
And here's what that race condition looks like in actual code. On the left, you've got a super simple counter. Now, that little count plus plus operation, it looks like one single step, right? But it's not. It's actually 3. First, read the value, then add 1 to it, and finally, write the new value back. The problem is, multiple threads can interrupt each other right in the middle of those steps, and you end up with the wrong count. The thread-safe version on the right uses something called an atomic integer, which guarantees that the entire read-add-write operation happens as a single, indivisible step. No interruptions allowed. Problem solved.
Okay, so how do we actually fix these kinds of issues? Well, it helps to think of it like having a toolkit for thread safety. And a really great developer knows exactly which tool to pull out for which job.
And here's a quick look at the main tools in that kit. You've got the classics, like synchronization and locks, which are kind of like putting a bouncer in front of your data to let one thread in at a time. We've got the atomic variables, which we just saw in action, and then you have some more advanced strategies like thread local storage, concurrent collections, and the one we're really going to zero in on today, immutability. Let's just touch on the most traditional tool for a second, the synchronized keyword. It is powerful, for sure. It creates what's called mutual exclusion, which is just a fancy way of saying only one thread gets access at a time. But, and this is a big but, that power comes at a really steep price. It can be a major performance killer, and if you're not super careful, you can create deadlocks where your threads end up waiting for each other forever, grinding your whole application to a halt.
But what if you could just avoid the whole fight entirely? That's the beautiful idea behind a stateless class. You see, if an object has no data that ever changes, no state, then there's literally nothing for the threads to fight over. A simple calculator service is a great example. Its add method only cares about the numbers you give it right now. It doesn't remember anything from the past.
And this brings us to a really crucial interview one-liner. Seriously, remember this one. If you're ever asked how to achieve thread safety, this is one of the strongest, simplest answers you can give. Stateless objects are thread safe by their very design. You've eliminated a whole category of bugs before you've even written a line of code to manage them.
So that idea of designing the problem away leads us to the most powerful concept in our whole toolkit, immutability. Instead of worrying about managing how things change, what if we just stop them from changing at all? And let's be really clear about this. When it comes to thread safety, immutability is widely considered the best approach. It's not just another tool in the box. It's a fundamentally better, safer way to design concurrent systems. So it's really important to understand why it's so powerful.
The definition itself sounds almost too simple. An immutable object is an object whose internal state cannot be changed after it's been created, period. If you want to modify it, what you're actually doing is creating a brand new object with the new value, leaving the original one completely untouched.
So how do you actually build one of these in Java? Well, here's the recipe. First, you make all your fields final, so they can only be assigned a value one time. You make the class itself final, so nobody can come along and subclass it to change its behavior. You provide no setter methods, no way to change the data. And here's a critical one. If you absolutely have to include an object that can change, you make defensive copies. That means you create a brand new, private copy of that object just for your class, so no one on the outside can ever get a hold of it and change it.
And here it is. This is the payoff. Just like those stateless objects we talked about, immutable objects are inherently thread safe. You can share them, pass them between 100 different threads, and you never ever have to worry about synchronization or locks because you have an ironclad guarantee that the data inside will never be corrupted. It simply can't be.
Now look, this isn't just some abstract academic idea. It is built into the very heart of the Java language itself. And for that, we can look at the perfect case study, the string class. I mean, have you ever stopped to wonder why one of the most common, fundamental building blocks in all of Java was designed this way? This right here is probably one of the most common and most revealing Java interview questions you can get. The answer isn't just one thing, it's this beautiful combination of thread safety, performance, and security. Nailing this answer shows you really understand core Java design. All right, so first and foremost, thread safety. In any real-world application, strings are everywhere. They're used for user data, messages, configurations, and they're being passed between threads constantly. By making them immutable, the designers of Java ensured this could happen without any risk of corruption, which has made life simpler for millions of developers.
Next up is a brilliant optimization called the string cool. To save a ton of memory, the JVM only keeps a single copy of each string literal. So if you have the word hello 1,000 times in your code, there's actually only one hello object in memory, with 1,000 pointers to it. This amazing trick only works because strings are immutable. Just imagine if they could be changed. Someone altering one reference would accidentally change the string for everyone else pointing to it. It would be total chaos.
This is a huge one, security. Just think about where we use strings. We use them for database connection URLs, for file paths, for security credentials. Now, if some malicious code could get a reference to your database password string and change it after you've already checked it, you'd have a massive security hole. Immutability gives you a guarantee. The value you check is the value you use. It cannot be tampered with.
And finally, performance. Because a string's value is guaranteed never to change, its hash code, which is basically a unique number generated from its letters, can be calculated just one time and then saved. It's cached forever. This makes strings incredibly fast and reliable to use as keys in data structures like a hash map, which are used everywhere.
Okay, let's pull all of this together. Knowing the theory is one thing, but knowing how to talk about it and what mistakes to avoid is what's really going to make you stand out in an interview.
So here are the common traps. First, don't ever say that thread safety just means slopping the synchronized keyword on everything. That's slow and dangerous. Second, don't think atomic variables are some magic bullet. They're great, but they only solve problems for simple single values. Third, Don't assume that creating new immutable objects is always bad for memory. As we saw with the string pool, it can actually save memory. And finally, don't just say string is immutable for one reason, like security. It's the powerful combination of all 4 reasons that makes the design so brilliant.
So, if you really want to leave your interviewer with a powerful, concise thought, here's the first half of a great closing statement. Draw this sharp distinction. Most thread safety techniques are about managing the problem of multiple threads changing things. Immutability is about eliminating the problem at the design level.
And this is the final, forward-looking point that ties it all together. This isn't just a clever trick from the past. It's the direction modern software engineering is headed. Building systems that are scalable, reliable, and easy to think about means favoring these simpler, safer patterns like immutability over complex, error-prone locking.
And we'll leave you with this question to think about. We've just spent all this time talking about how powerful and elegant immutability is, but in a world of complex performance trade-offs and constantly changing state, is it really the right tool for every single job? The real answer, as it always is in engineering, is it depends. Thanks for tuning in.
So, let me ask you something. You ever had a background task in your Java app just stop? I mean, no errors, no crash, it just vanishes into thin air. If that sounds familiar, you're definitely not alone. Today, we are cracking that case wide open by exploring the secret world of Java's daemon threads.
All right, let's set the stage for our little investigation here. We're looking at a scenario that trips up a lot of developers. Just think about it for a second. You've written some code for, logging or maybe monitoring something, maybe some kind of cleanup task that's supposed to run in the background. You fire up your application, everything looks great, and then, poof, your background job is just gone.
And that's what makes it so weird, right? The rest of your application, it finished its work perfectly. You're checking the logs and there's nothing. No exception, no emergency exit. It's like a ghost in the machine. So what is going on here?
Well, it's time to introduce our prime suspect. It's a special kind of thread that loves to work in the shadows. We like to call it the silent servant.
So this is the official definition, the one you'd want to have in your back pocket for an interview. A daemon thread is basically a background helper. Its whole job is to serve the main user threads. But here's the absolute key piece of evidence. It does not stop the Java virtual machine from shutting down. Let's break that down a bit. Daemon threads are designed for non-essential stuff, housekeeping tasks. Think of them as the roadies for a rock band. They're working while the main show is happening. But, and this is so important, there is zero guarantee they'll finish what they're doing. The second the main show is over, boom, the lights go out and they're done. Now, to really understand our suspect, we've got to put it in a lineup next to its counterpart, the user thread. The difference between these two is the secret to this whole mystery.
This table just lays it all out, crystal clear. User threads, like your main method, they're the stars of the show. They are the core logic. And the JVM, it'll wait patiently for every last one of them to finish before it goes home. But daemon threads, nah. They're just for background services, and the JVM completely ignores them when it's deciding whether to shut down. And that means their completion is never, ever guaranteed.
If you only remember one thing from this whole explainer, make it this sentence. Seriously, this is the perfect one-liner. User threads are the life support system for the JVM. Once all of them are gone, the machine powers down, and it doesn't matter what any daemon thread was in the middle of doing.
Okay, we've arrived at the heart of the matter. This is the one single rule that explains everything about why our task just vanished.
This is the fundamental law of the JVM. It's a very predictable system. It waits for every single user thread, all your main logic, all your request handlers, to wrap up their work. But there's a catch.
And there it is. That's the motive. The JVM just does not care if a daemon thread is halfway through writing a file or updating a metric. The moment that last user thread signs off, the JVM just pulls the plug. The lights go out, and any daemon threads still running are terminated right then and there.
So what does this actually mean for you? Well, the implications are pretty severe. It means any line of code in a daemon thread can be stopped dead in its tracks. And get this, even a finally block, the thing we always rely on for cleanup, is not guaranteed to run. This is why you must never, ever perform critical work, like writing to a database or a file inside a daemon thread. It's a recipe for disaster.
Okay, mystery solved. Now let's look at where these silent servants actually show up in the real world and a few common traps that developers often fall into.
The funny thing is, you've been working with daemon threads this whole time, maybe without even knowing it. The most famous one is the garbage collector, always running in the background, cleaning up memory. It's the perfect example of a non-essential task. I mean, the JVM isn't going to wait around for a full GC cycle before it shuts down, right? This is the #1 example to bring up in an interview, by the way.
So how do you make one yourself? It's really simple, but there's a critical catch. You create your thread object, same as always. Then you have to call setDaemon true before you call start. That order is non-negotiable. If you try to change its status after it's already up and running, Java will just throw an illegal thread state exception at you. So yeah, order is everything here.
All right, let's bust a few myths real quick. First, daemon threads are not guaranteed to be low priority. The spec doesn't say that. Second, and we've hammered this home, the JVM absolutely does not wait for them. And third, and this is the big one, never, ever put important business logic in a daemon thread. It's just asking for trouble and potential data loss. So we've covered the what, the why, and the how. Let's wrap this all up with one final golden rule that perfectly summarizes everything we've just learned.
This is it. This is your powerful closing statement, the perfect summary. Daemon threads are your background helpers. They do the support work. They won't keep the app alive, and because of that, you can't rely on them to finish. Use them for things that are okay to abandon midway, but never for anything that absolutely has to complete.
And that brings us to the final question, and this one's for you. I want you to go back and look at your own projects. That little background task you wrote a while back. Did you happen to set it as a daemon? Could it be the next victim in one of these mysterious disappearances? Now you have the tools to be the detective.